Hello, so I'm going to talk about central limit theorem for a wide range of statistics in classes of graphs that are called subcritical. So this is a joint work with Dimbinaina, Ralaivaosaona from Stellenbosch University, and Stephan Wagner, which is with me at Uppsala University. And so what is a block? So a block in a graph is a maximal, in terms of inclusion, two connected components. Or it can also be a cottage, so it will be a degenerated block. So there is a famous decomposition of graph according to in blocks according to cut vertices. So the cut vertices here are in red. And so if we cut the graph along the cut vertices, then what is left are the blocks. And we will be interested in classes of graphs that are called block stables. So it's a very natural class of graphs. So it means that if I have a graph in my class is block stables if all the blocks of this graph belongs also to the class. So typical block stable graphs are trees, planar graphs, triangle free is block stable, but a class of graphs which, for example, all the graphs with a path of length at least k will not be block stable. So block stable graphs, we study them because they are amenable to being encoded easily by generating function so that we can count. So here we'll have the generating function of, so we will restrict ourselves to connected classes of graphs, but all the results we do here, we can extend them easily to non-connected graphs. So here will be the generating function of connected graphs. So little cn will be the number of connected graphs on n vertices. And we only deal with labeled classes of graphs. So we divide by n factorial. And so b of x will be the generating function of the blocks in the class. And so if we look at the block decomposition, in terms of generating function, this can be translated by a functional equation. So this is, so we need to do this decomposition, we need to root at a vertex. And so along this vertex, we'll have several blocks attached to it. So we consider the generating function of rooted connected graph in the class. So this will be equal to, so a vertex, x, times a set of blocks that are also rooted at this vertex, but we forget the label of the root. And on each of these blocks, on every vertex, we paste a connected graph rooted at this vertex. So this looks like that. So this notation C dot, so when the dot is black, it means that we root, so we differentiate, distinguish a vertex, and then we put the label back of the vertex. And so famous block stables classes of graphs. And so we have the classes of trees where the blocks are single edges. And so the generating function of the block here will be just a single edge, so x squared over 2. So we have two vertices, an edge, and it's not rooted, so we divide by 2 because of the symmetry in the two possible labelings of this edge. And then this functional equation for trees is transformed into the famous equation for trees. Then we have cactus graphs where the blocks are cycles, so convex polygons. So here the generating function of the blocks is either it's a single edge or it's a cycle. So this is all the possible labelings. We divide by 2 because we have two possible, we have a symmetry in the n-1 factorial possible labelings of this n cycles. And this is the functional equation is translated like that for cactus graphs. Now block graphs, this is the class of graphs whose blocks are cliques. So complete graphs on k vertices. So for every n, there is a unique complete graph on n vertices, and which it has a unique label. And so the generating function of blocks looks like that. It's an exponential, and the functional equation translates into this one. Then there are other classes of graphs where the generating function of blocks cannot be written explicitly. It can only be written as a solution of a system of equations, a recursive system of equations, but they are still very interesting to study. So we have the outer planar graphs. So these are the graphs for which the blocks are dissections of convex polygons. So dissection of a convex polygon is you take a convex polygon and a subset, non-intersecting subset of diagonals. And then the series parallel graphs, which are the blocks are a series of parallel compositions of blocks. Well, it's a kind of technical detail, but it's a recursive definition for the blocks. Now, subcritical families of graphs. So we consider still connected label graphs, and we say that such a class of connected label graph is subcritical if, from the two generating functions we saw before, the generating function of the connected graph and of the blocks, we see them as complex function of the complex variable. And so if they are analytic in a disk of positive radius around the origin, so suppose that rho is the radius of convergence of C of x and eta is the radius of convergence of B of x, then the class is called subcritical if we have the following identity. So we have that the C dot, the generating function of connected graph rooted at a vertex, evaluated at its dominant singularity is strictly smaller than the singularity of B. So there is an alternative form which might be a bit easier to see. This comes from the functional equation we saw before, due to the block decomposition. So if the following system here of two equations admit a positive solution, rho and gamma, which is C dot valued at its singularity, which is strictly smaller than the singularity of the blocks, of the generating function of the blocks. So this comes from here. This is the direct translation of this functional equation. So subcritical families of graphs are huge. There's a lot of famous classes of graphs inside, so that have been widely studied. But the first paper, the seminal paper, who studied this as in full generality, just as subcritical classes, was this paper from Darmota, Fuzzi, Kang, Krauss, and Roy. So it tells us that if we have a subcritical classes of graphs satisfying this identity, then the generating function connected graph rooted at a vertex has a local expansion around its dominant singularity of square root form. And so we also have equations to compute those coefficients here, gamma and gamma 1. So they depend on the derivatives of the successive derivative of the generating function of the blocks. And we have, so this local expansion allows us to enumerate any subcritical family of graphs, and they all look like, so the unrooted version looks like this. Always the asymptotic of the coefficients always looks like that. So this is just an application of the transfer theorem. Now, subcritical families of graphs, they are essentially tree-like. They look like trees. When we look from far away, this has been formalized in 2016, so by Panagiotto, Stuffler, and Vela. So tell us that the scaling limit of a uniform random graph in a subcritical class is actually the continuum random tree. So sadly, subcritical families of graphs, they don't have, so it seems that we will never have a satisfying characterization in terms of purely graph theory. It's because of this recent result from Georgakopoulos and Wagner, telling that actually every proper minor closed family of graphs that you can think of will be contained in a subcritical class of graphs. Anyway, so to the heart of the subject, now we will be interested into very particular statistics when we consider the random graph into our class of subcritical class. Those are called block statistics. So first you take a weight function that takes a block and sends it to an integer. And then for a given weight function, the block statistic associated to a graph in our subcritical class with blocks B1 to Bk will look like that. So it's the sum of the valuation, so of the weight function on each of the blocks of our graph. So examples of block statistics. So we have trivially, if we set all the weight function, which is one for every block, on every block, then the block statistic will be the number of blocks in our graph. we'll also have that. So for example, if we fix a two connected graph, and the weight function will be 1 if this connected graph is isomorphic to our block, or 0 otherwise, then this is the block statistic, exactly the number of occurrences of this graph into this subgraph into our graph. So interestingly, we also have, so suppose that tau of t is the number of spanning trees in our graph. Then we define the weight of a block as the log of the number of spanning trees in the block. And then the block statistic will also be the log of the number of spanning trees in our graph, because the number of spanning trees in the graph is multiplicative with respect to the blocks. Actually, this can be generalized to any special value of the third polynomial, because the third polynomial is also multiplicative over the blocks. So if our weight function is a special value of the third polynomial, then the block statistic will be the log of the number of this value of the third polynomial. So for example, the log of the number of subforests, spanning subforests, acyclic orientation, and so on. So the block statistics are quite a wide range of statistics in subcritical graph classes. So now to encode it, we still use generating functions. We still want to count. So now we use bivariate generating function, and we mark the variable of the blocks like this, so exponential of the value of the block statistic for a connected graph, and then the variable that carries the statistic. So we do the same for the generating function of blocks, bivariate generating function of blocks. The block decomposition directly translates into, so bivariate functional equation scheme. And now this is where the problem becomes a bit interesting. So if there is a block, if there exists a block such that the weight function grows faster than linearly, so superlinearly, then the radius of convergence of the generating functions involved can become 0. And so it becomes not so easily amenable to analytic combinatorics, to singularity analysis. And so, what are some results known on statistics in block statistics in subcritical graph classes? So now in the rest of this talk, capital C sub n will be a uniform random graph taken in a subcritical graph class on n vertices. So the first results, so just general central limit theorems on this, that so if you restrict yourself to only planar classes of subcritical graphs, then both the number of edges and the number of blocks satisfy a central limit theorem as n goes to infinity. So the proof, so I'll try to go briefly on the proof. So if so here, yes, so here, because of planarity, the number of edges will always be linear in the size of the block. And so our weight function will be linear in the size of the block. And in this case, then the dominant singularity of the block function will change continuously with the parameter t. And so we will have that this subcritical identity, the characterization of subcritical graph classes, this equation remains true also for every t in a neighborhood of 0. So there is classical theory, notably due to Michael Darmota, that the result on perturbation of functional equations. So then we will also have, so the bivariate local expansion of the generating function of connected graphs with that vertex will also have a square root singularity. And then we can compute the moment generating function associated to our block statistics. We use the asymptotic formulas given by the transfer theorem in both cases, and then we have so the moment generating functions converge to this quantity, which is exactly the hypothesis of the quasi-power theorem, and then we directly get the central limit theorem. So that's what they do. But what to do when we have statistics, block statistics that are not linear? So an example will be if you consider the class of block graphs. So here we are not planar anymore. And so just the number of edges in a block is the size of the block just 2. So it's quadratic. Then here, if you look just at the log of the number of spanning trees, then it's at the order n log n. And then it's similar to many values, special values of the third polynomial over the blocks. Then so there is a notable result. The only result that we know of on superlinear block statistics. As a general, if you take the number of occurrences of a fixed two-connected subgraph, this has been proven in a subcritical graph class, then this also satisfies a CLT. So to solve this, they had to design an infinite system of equations. But we do something different. We prove something a bit more general, and we have something a bit different. So suppose that you have a block statistic given by a weight function W, and you want that the limit sup of the average of W squared over all blocks, the limit sup of the n square root of this is strictly smaller than eta over gamma. I will repeat, gamma is the univariate function of the blocks, the univariate generating function of the connected graph with the vertex. It's the valuation of its dominant singularity. So if we are in this context, if we have a block statistic satisfying this, then we prove that the block statistics, the expectation and the variance are linear, and we can compute also. We give a way to compute those coefficients here, and also the lambda here, but I didn't put it. But there is also a formula computing the lambda in the expectation here, and the variance. Of course, the variance here could be 0. But if it's not 0, so we have a characterization with respect to the derivatives of P, and this gives us this characterization. So basically, if the weight function is not, for uniform constant C, is not at the same size as the block itself, then for every block, then the variance then will be non-zero, and then we have a central limit theorem. So I will just do a brief, show you some ideas to prove the CLT. So here we cannot use the classical theory that I showed you before because we are not linear. The weight function doesn't have to be linear, it's more. But instead we take a truncation. So we truncate the weight function. We say that it's for a given integer m, it will be, if the block has size m or less, then we take the normal weight function and it's 0 otherwise. So this truncated weight function has finite support. So we can write the generating function, the bivariate generating function of blocks like this. So we take all the blocks that are not in the finite support. So here the value of the weight function will be 0. So it becomes kind of this univariate generating function. And here, this will be the function, the generating function summed over all blocks that are in the support, so where the weight function is not 0. And so we can rewrite this as the univariate generating function plus a finite sum, which the finite sum is an entire function. So it's amenable to classical analytic combinatorics. And by a very similar argument that the one I showed you in the linear case, then we know that the truncated block statistics resulting from the truncated weight function associated with the truncated weight function satisfies a central limit theorem with linear expectation and variance. And now, if we show that, so there is a result in probability theory that we use, and its hypothesis is that if the normal law with this parameter converges in distribution to the standard normal law, then, and also the variance of this quantity here, so minus this quantity here, is bounded and converges to 0, is uniformly bounded and converges to 0 as n goes to infinity, then we have a central limit theorem. So this is the hard part to show in some sense, but this is basically the idea. Okay, so what we can show is a central limit theorem for a wide range of parameters in subcritical graph classes. It always has linear expectation and variance. So example for block graphs. So we show central limit theorem for the number of edges, the log of the number of spanning trees, and non-trivial complete subgraphs. And interestingly, for example, for series parallel graph, we can show that also the log of the number of spanning trees is log normal, asymptotically. So there was a paper from Ehrenmüller and Ruwe that's saying that the expectation satisfies this estimate. And no, of course, they couldn't find a central, they couldn't prove the limiting distribution. So we prove that it's like normal, but we cannot compute the coefficients because there is no good encoding. We don't know any good encoding of this problem, so of this parameter with generating function. So we just prove the limiting distribution. So possible extensions of this work would be to extend to prove log normal asymptotical log normality for other block statistics that are not block statistics. So typically there will be the number of matchings, the number of independent sets, perfect matchings, etc. And this should be interesting to also prove asymptotic log normality, but of course we have to listen to different methods. So I will stop here. Thank you all for watching.